Hey everybody, today we're going to start in on the Discrete Random Variables chapter, and as is usually the case here off the top of the chapter, I give us a reminder that I do have dedicated and focused videos on individual topics all the way through. Today we're going to be talking about these first couple of things: an overall introduction to discrete random variables. A discrete random variable has a discrete probability distribution, so those things go hand in hand, and the expected value and variance of discrete random variables. Very important thing, characteristics of the distribution, and we're going to look at that. If you prefer me talking with you like this, that's great. If you want the more dedicated, focused, tighter videos, feel free to watch those instead. Either way is fine by me. Okay, so we are working through the before notes on all of this, and let's just get to it. So first of all, this is really important. This is setting us up for the things we are doing later when we're trying to get to inferential statistics. I keep reminding us of that, and that is what we are trying to do. We're going to get to inferential statistics. But we still need some of these ideas, these probability ideas, these probability models in order to draw inferences about our population parameters. So we had a probability section, but probability is going to come up for the remainder of our work together because when we're trying to draw inferences about population parameters based on sample statistics, there's always going to be some sort of probability statement involved. There's always going to be some sort of probability model that we're working with. And so here we're going to talk about, just the general case and then the specifics of discrete random variables. So concept of random variables, first of all, extremely important. It's the basis for what we do, how we go about this thing where we try and use sample statistics to say things about population parameters. And the overall notion is that we're going to view sample statistics as random variables. So in casual terms, that means their value is going to be partly determined by chance because we are going to be doing things like sampling from a population. So I think we have some sort of intuitive notion of these things where if we sampled the 10 students from a university and measured their average height, fine, we'd get a value. If we sampled another 10 students from that university and got their average height, we'd get a different value. So these statistics that we're collecting are going to, the value of these statistics is going to change from sample to sample according to some probability distribution of the statistic. And so that's going to play a fundamental role in how we view statistics and how we go about trying to say something about population parameters from them. So informally, and this is good for, I think, a good way to view it for applied introductory statistics courses, that a random variable, a quantitative variable, whose value that we observe is partly due to chance. You sample a bunch of porcupines, you get their average weight, right? If you know going in that if you sample some different porcupines, you get a different average weight other than by fluke. And so that average weight is partly due to chance. And so a random variable is going to be a quantitative variable, and its value is due to chance. Now, there's formal mathematical ways we have of doing this. So this is really formal and strict mathematical discussion. Might phrase that a little bit differently, but I think for what we are doing in applied introductory statistics, that's a pretty good way. Okay, so a couple of basic examples. Start off with some trivial things like we do in probability. We're about to toss a coin 10 times and count the number of heads observed. Well, the number of heads is a random variable. So we toss it, we're going to get a certain number of heads. That number of heads might be 0 or 1 or 2 or 3 or 4 up to 10. And depending on the coin and our specific assumptions, there would be certain probabilities of those outcomes. But going in, say, okay, we're going to toss this coin 10 times. That number of heads that occurs, that's a random variable. And because it's partly due to chance. Its value is partly due to chance. And when we actually carry out this experiment, we actually do the tossing, it's going to take on one of those values. Now, in the real world, when we get back to applied stats, we're going to be doing things like this, right? We're about to sample 30 adult male porcupines of a certain species, say, measure their weights. Then each of those individual weights would be a random variable because there's some randomness associated with how we sample these porcupines. You get a different porcupine, you get a different weight. So there's some randomness associated with that. Their individual weights, as we're about to randomly sample a porcupine, that weight that we get, be a random variable. So those individual weights of the 30 adult male porcupines are random variables. Once we get the porcupines, they take on certain values. And then quantities based on those numbers, like let's say the average weight, that it too will be a random variable. And once we get our sample, and measure the weights, that sample mean is going to have a value, right? Take on a value, 8.2 kilograms or whatever we end up getting. Okay, so those would be like random variables. Now, conceptually here, we're not going to know the value of the random variable until we actually carry out the experiment, can make our sampling design, do this sort of thing. We actually take the observations in whatever way we're going about that. We're not going to know the value of the random variable. We might conceptually know what it is. We're about to toss a coin 10 times and count up the number of heads. Conceptually, we might know what it is, but it doesn't take on a value until we carry out that idea. And so we don't know the value it's going to take on, but we might know characteristics of the distribution, like what values it could take on and their probabilities of occurring. We might know that, or we might make certain assumptions about it. And so the distribution of a random variable is going to play a very fundamental role for us in how we construct our statistical inference procedures. And we usually represent random variables with capital letters near the end of the Roman alphabet, capital X, capital Y, capital Z, capital U, capital T. We can do these sorts of things. Depends on our needs, but it's usually towards the end. And depending on the notation in typical courses or textbooks, we usually start with either X or Y. I'll just start with X for the stuff we're doing. Typically, if there's 1, we'll call it X. If there's 2, maybe X1 and X2, maybe Y. But capital letters near the end of the Roman alphabet. And one thing here that might be a little bit subtle, perhaps, and some people try and avoid it in the notation, but I just think any attempt to avoid it just results in more problems than it helps. So we're going to draw a distinction between the random variable, like the random variable X, say a capital X, which is a theoretical quantity, the number of heads we get when we toss a coin 20 times, say, and the value that it will eventually realize, the realized value, that once we toss the coins and count up the number of heads and get 15 or 7 or whatever it is, this realized value of the random variable. So we let the capital X typically represent the random variable itself, and a lowercase x represent a realized value of the random variable. So this might be a bit confusing at times. Not a huge deal if you don't quite get it, but it's just something that someone like me needs to take into account when I'm writing stuff up. But we might say something like this: the probability the random variable x takes on the value little x. That might be a point of interest, or just a probability the random variable x takes on the value 6. Say the probability we get 6 heads when we're tossing a coin 20 times, or whatever it is that we're interested in. So this little x is going to represent like a generic value that the random variable eventually takes on. Okay, so we have this distinction between discrete and continuous random variables. And I'm drawing sort of a clear line. I'm saying random variables can be either discrete or continuous. They could have mixes and various sort of other possibilities. But for us, and the big distinction is between these two, because we're going to have discrete probability distributions, we're going to have continuous probability distributions, and we're going to have to handle them a little bit differently due to their nature and the mathematical models we use. And so we're drawing this distinction here, although there could be sort of others, like a mix between the two or various things like that. But it's important that we understand this distinction. So discrete random variables have what we call a countable set of possible values. Now, I hesitate sometimes whether or not to put that in there, because countable has a very specific mathematical meaning in that they're mapping to the natural numbers, right? So I'm putting it in here. There is a very mathematical meaning for that, and why I'm bringing that up is it doesn't necessarily have to be a count. When I say countable, I'm not saying it's necessarily a count, like a random variable might represent a count. It doesn't have to represent a count. But we'll look at some sort of more casual examples here. There's a formal mathematical definition of this that I'm not going to get into. Continuous random variables take on an infinite number of possible values corresponding to all values in an interval or intervals. So a continuum of values, whereas these discrete random variables are going to have jumps between the values. So it might be helpful to have a little look here at the visual here. So these first ones up top here, I have discrete random variables. So 3 discrete random variables off the top. And this particular one, right up here, I'm saying there's only 3 possible values of x. X takes on the values 0, 1, or 2. Those are the 3 possible values of x. It takes on the values 0, 1, or 2. And take on a random variable can take on any one of those values, and there's spaces between there. Casually speaking, there's jumps between 0, 1, and 2, and those are the whole numbers. But what I'm getting at over here, or those are whole numbers, right? 0, 1, and 2. They don't have to be whole numbers. Doesn't have to be whole numbers. Like over here, I have a similar type of thing. Let's say x, the random variable x is taking on these values, the little x values of minus a half, 1.8, 2.2, but it's still discrete over here. We've got these discrete jumps between these possible values that are in yellow here. These discrete jumps between the values. It takes on 4 possible values, so that's a countable number of possible values, and up here this is also discrete. Now, discrete random variables can take on an infinite number of possible values. So the distinction is not simply infinite versus finite. That is not the distinction between discrete and continuous random variables, because we might have situations, and often do, where our random variable can, let's say, take on values 1, 2, 3, 4, 5, with no upper bound. So it can just keep on trundling off to infinity there. And so there's an infinite number of possible values in this case, but it's still discrete because we've got these discrete jumps between the possible values, and then there's that technical mathematical notion as well. Might be a little bit easier if we look now and compare this to continuous random variables. So continuous random variables here, and we'll look at those after we get through talking about discrete for a little while. Continuous random variables can take on any value in an interval or intervals, but typically we'll have one interval here, a continuum of possible values, and that's always going to be infinite. So there's going to be an infinite number of possible values for a continuous random variable because it's taking on any value in an interval. So here, all the values between 0 and 1, so 0.378924568 pi by 4, right? Anything in there between 0 and 1, and there's an infinity of possibilities between 0 and 1. So here, your random variable would be taking on any value, a continuum of possible values. Similarly, over here, it doesn't have to be between 0 and 1, and it could be negative values. And here, same idea, really, same idea. I'm saying it takes on all values, or the random variable can take on any value between -0.5 and 2.5. So this would be a continuous random variable again. Or, the continuous analog of what we had up here, where it's taking on anything greater than 0, but smooth any value between that is greater than 0. So 38.7924894, right? Right? Pi squared, these sort of things. So there's going to be a difference between how we handle these mathematically. And so we have to talk about them separately in a sense, although there'll be very many similarities between how we handle these. Similarities will abound. Some differences will be necessary. Well, some differences exist and we'll necessarily have to handle them differently. So, okay. Couple of more concrete examples here. Number of broken eggs in a randomly selected carton of a dozen eggs. All right. So that can be 0, 1, 2, 3, up to a dozen, right? If we're talking about the number of broken eggs, we might let that be represented by the capital value x, the random variable x. We're about to grab this randomly selected carton of eggs and say capital X is going to represent the number of broken eggs in there. That's a discrete random variable, right? We could think of the possible values of my random variable x. What would that be? Well, 0 is one possibility, 1's another possibility, 2, and if your carton is really smashed up, you might have 12 broken eggs. And those are our 13 possible values of our random variable. 13 possible values of our random variable, and so that's a discrete random variable. And down here, like some of those examples we looked up top, if we look at the number of tosses until heads first appears, well, sort of a similar setting up here when we're talking about broken eggs, because we're still talking about a count, but it's a little bit different. So number of tosses until heads first appears. Again, we could let that be represented by capital X, or we could let it be represented by capital Y if we wanted. And what are the possible values? Well, we could get heads on the very first toss. So Y might take on the value 1. We just get heads on the first toss. Took us one toss. Or we might get tails and then heads. Or we might get tails a couple of times and then heads. And we could just keep flipping tails, right? For a long time. It's only in the absolute limit as this number of tosses goes to infinity where we must get heads eventually. But it's non-zero probability of getting, even in the tosses of a fair coin, non-zero probability of getting a trillion tails before getting your first head. So this goes off to infinity. So there's infinite possible values of our random variable y here, but it's still a discrete random variable. Y is a discrete random variable, like x was a discrete random variable. We've got these little jumps between the values. It's not a continuum of possible values. And so often, the things we're dealing with in the real world, often discrete random variables do represent counts of something. But they don't have to represent a count. It doesn't have to be a count. It doesn't have to be whole number values. It can have decimal places, this sort of thing. So let's say if you're betting a friend 0.25 cents or a quarter, right, that heads will come up when a coin is tossed. Well, your profit on the wager, if we're measuring it in dollars, say, is either going to be minus, right, 25 cents, or, plus 25 cents, or like $0.25 if we wanted to phrase it that way. And so don't get drawn into this strange idea that discrete random variables can't have decimal places or that kind of thing. That doesn't have to be a count. Will be fairly often, but discrete random variable definitely also quite often does not actually represent a count of anything. It's just discrete in its nature. We've got these jumps between its possible values, and it is in that mathematical sense that there's a countable number of possible values. Okay, so continuous random variables. We often see this in things like weights and times and heights and lengths. Those things are in their nature continuous. So I once was, when I was born, 10 pounds, 6.5 ounces, as my mom told me about on a number of occasions, 10 pounds, 6.5 ounces. I'm now about 100 kilos. I have gone through every single weight between them in my life, right? At one point in my life, I was between those two weights. Right, I had to pass through them all. So, right, so that's at one point in my life, I was, everything in that smooth continuum between there. And so, in its nature, weight is going to be continuous, and height and time and these kind of things. Now, what you might be thinking, hey, wait a minute. This is going to be subject to the vagaries of our measuring device. And let's say we only measure weight to the nearest kilo, and then you got 1 kilo and 2 kilos and 3 kilos. Good point. Okay, yes, at some point we're going to be taking a measurement and not going off to infinite decimal places. True. But we typically think of this continuous in terms of its nature, that the nature of weight is continuous. The nature of time is continuous. You could just keep chopping that up in finer granularity there, right? And so there's that smoothness in there. But absolutely, there will be some restrictions and rounding imposed by our measuring device, whatever it may be. So, hello, Charlie. Very sweet dog. Thank you, Charlie, for leaving. Okay. So time here. Time until a randomly selected light bulb fails. Again, we might call that capital X, right? We might call that capital X. And then we might say the possible values. Let's say anything bigger than 0. And we could quibble about 0 being in there, but we might say the values that X can take on, when we have our little probability models, we might say that's just like bigger than 0. Right? Or we could quibble about whether 0 is included in there or not. It's already failed or what have you. But it's going to be something like this. In this case, we have that the values X can take on any value bigger than 0, whether we're measuring it in seconds, days, weeks, eons, whatever it is we're measuring, right? It'd be something like that. And similarly, the weight of a randomly selected newborn male at a certain hospital. There's going to be some variability in there. Now, the weight itself is continuous, but of course subject to some sort of rounding due to the nature of the actual weighing, etc., etc. But we would typically think of the weight itself as being continuous, a continuous random variable. Okay, so mathematically, we're going to have to handle these situations differently, and we're going to talk about discrete random variables for a while and then get back to continuous and see the similarities and see the differences. But before we talk about get into discrete, just take a look at a couple of things here. And I have two probability distributions. So random variables are always going to have a probability distribution of some nature. And for us, we're going to have discrete distributions. We're going to have continuous distributions. And discrete distributions are going to look something like this. So the distribution of the number of heads in 25 tosses of a fair coin, well, the number of heads we get is going to be any whole number between 0 and 25, right? I didn't put 25 here just for visual purposes, but there's a 25 out here. And on the vertical axis, we often have the probability. So we might call this a probability histogram. And we'll talk a lot about how we come up with this. But right now, just think of this. This is a discrete probability distribution. First, note that there are these jumps between the possible values. 0, 1, 2, 3, 4, 5. And in the histogram here, for the probabilities, we see these jumps, right? It goes from 6, and then the probability of 6 is there, and then boom, probability of 7, probability of 8, probability of 9, probability of 10. That sort of idea. We're getting these jumps in these probabilities between these different values. For a continuous distribution, similarities, but some fundamental differences. So this is approximately the distribution of the height of adult Canadian males. And we have the values of the variable down here, like we had the values of the variable up here, right? The x-axis is going to represent values of the variable, but it's a continuum now. Height is a continuum, right? So take on any value, plausible value here. And if our measuring device is precise enough, we could keep going off to a large number of decimal places. You might notice I didn't put anything here. And I did that intentionally because we're going to talk about that at another time. But what to note now, that's not a probability. That's not a probability. That's not a probability. The vertical axis in these distributions is not actually going to represent a probability. And in the time, we'll talk about this when we get to continuous random variables. But for now, for continuous random variables, it's going to be important when we get there, but probabilities are going to be found from areas under the curve. That's going to be the important thing. So, but you don't need to know that now. We'll discuss that in detail when we get to continuous random variables. Thing to note here is we've got this nice smooth curve for continuous random variables, smooth curve of some nature. And for discrete random variables, we've got these jumps. And discrete mathematically is going to be a little bit easier to handle, but won't be so bad with the continuous because we'll rely on software to do some of the grunt work for us. Okay, let's look at a specific example here. Center for Disease Control and Prevention tells me that about 3% of newborns in the United States are born with major structural or genetic defects. And let's say we're about to randomly sample 2 United States newborn babies. And I'm going to let X represent the number of these newborns that have major structural or genetic defects. So first of all, let's list out the possibilities here. This is my possible outcomes. My outcomes in my sample space is that the first individual I look at, the first baby sampled, has these major structural or genetic defects, and the second one does as well. That's the first outcome in my sample space. In this second possibility, the first one I look at has major defects, and the second one does not. So I'm letting N represent them not having it. I could put D complement or something like that. I'm just putting in D. They do not have these defects. Similarly, the first might not have it, and the second one does, or they both do not have these major structural or genetic defects. Well, the X is defined. We've defined our random variable to be the number of these 2 newborns that have these major structural or genetic defects. So this is what's doing here. This random variable is mapping these outcomes to some sort of number, right? And we're saying, okay, well, in this particular case, it's the number of these individuals that have these major structural or genetic defects. So NN, nobody has it. ND1 has, and DN1 has, and DD2. So the possible values of my random variable X, I know that, right? My possible values of my random variable X are 0, 1, and 2. So these are the possible values. And I'm going to put these in table form and then say, hey, we can figure out the probabilities of those. So I've got a little x here, little x representing the possible values of my random variable X, 0, 1, and 2. And we're going to work out the probability the random variable X takes on the value little x. So this is common notation for us. The probability the random variable X takes on the value little x. Short form, I will use short form for this sometimes as little p of little x. When I say little p of little x, I mean this. This is a little bit more explicit. The probability the random variable X takes on the value little x. So in other words here, right, that's going to be the probability X takes on the value 0. Over here, right, probability X takes on the value 1. And here I'm going to find the probability X takes on the value 2. Okay, well, we can do this with basic probability rules. If we're randomly sampling 2 U.S. newborn babies, and we're doing this in such a fashion as random sample or randomly and independently sampling from the population of newborn babies, this sort of thing, each individual one, there's a 97% chance they do not have these major defects. And if we're doing this random and independent sampling, then these outcomes are going to be independent. So the probability that we get no defect and no defect 0.97 times 0.97. Remember, for independent events, to find the probability they both occur, we can multiply their individual probabilities together. Similarly, over here on this other side, this one's easy as well, right? On the 2, that's getting the defect and the defect. So same argument, 0.03 times 0.03. And a little bit trickier is the 1. But note that for the 1, it happens in these 2 ways, right? You get the defect and then not, or not and then the defect, and we have to figure out the 2 of those and add those probabilities together. So that's what's happening here, why I'm doing that. So what do we do here? We listed out, defined a random variable, we listed out its possible values, and we found their probabilities of occurring. And that is what we call the probability distribution of the random variable X. We have this listing of the possible values of X and their probabilities of occurring. Okay, so this probability distribution of our discrete random variable X, we can call this, write this up in different ways, but we're going to say it's a listing of all possible values of x and their probabilities of occurring, like I just said. And we could express this in different ways. Maybe the table, but the table's not going to work very well if we get a large sample size, right? Conceptually, the same idea for n is 2 as n is 1,000. But if I had 1,000, randomly sampling 1,000 babies, which we might want to do for some statistical inference scenario, then it's going to be extremely cumbersome and not really practical to list out all those possibilities in a table. So we have a couple of ways of doing it. We might have this nice functional form for it, or the formula type of thing, where things fit nice and simply into something like this. And this is something we call the binomial distribution. I don't expect you to fully understand this right now or even understand it at all. Just know that sometimes we have formulaic ways of expressing the probability distribution. Or we might draw it out in a probability histogram like we did for the other one. One problem for a probability histogram, right? The probability of getting 2 is really small. It's not 0 there, but it's kind of hard to tell, right, what's going on. It might be a bit misleading at times. But probability histograms are very legitimate things to draw out. So we had this, where we had this table form, and we had this formulaic form or probability histogram. All of those represent the distribution of our random variable x. But we have different ways of representing the distribution, and more on that in a second. There's a couple of characteristics any discrete probability distribution will have to have. So there's a couple of characteristics. One, basic notion, all probabilities must lie between 0 and 1. We've had this before. We know this from basic probability, so it's no different here. So if it's going to be a legitimate probability distribution, all those probabilities, all the probabilities in there, have to lie between 0 and 1. And since it's a listing of all possible values of x and their probabilities of occurring, one of those values of x is going to happen, and so those probabilities must sum to 1. So if we have something where these two are not satisfied, then it can't be a legitimate discrete probability distribution. Note we're talking about the probabilities here. The probabilities have to lie between 0 and 1. The probabilities have to sum to 1. The values of x could be negative or fractional or minus a third. These sorts of things. It's the probabilities that we have these restrictions on for just basic probability notions from when we talked about basic probability. Now, there are a variety of ways of expressing a distribution. Depending on how deep we wanted to go into mathematical statistics as we trundle along, we can talk about a variety of different ways that of expressing a distribution, different types of functions that uniquely determine the distribution. So when we say distribution, we're talking about all the values your random variable can take on and their probabilities of happening, but we can write about that in different ways. So the function that yields the probabilities for a discrete random variable, we call the probability mass function. So the function that gives us these values, the probability the random variable x equals little x for all values of x, that's called the probability mass function. And we have another way, though. You might think, well, that's just the distribution. Well, sure, we can think of that as the distribution. The probability mass function uniquely determines the distribution. But there's other functions that also do. So another thing we have is the cumulative distribution function. And that we typically label as capital F of x. So f of little x, capital F of little x. And that, by definition, is a function that gives us the probability the random variable x takes on a value less than or equal to little x for all x. This is the cumulative distribution function, the function that gives us the probability the random variable x takes on a value less than or equal to little x. And this also uniquely determines the distribution. And these two, we could go back and forth. You can get the cumulative distribution function from the probability mass function, and vice versa. So both of these things would uniquely determine the distribution. And there's some other functions, like moment generating functions, beyond the scope of this course, that also do. So what we had up top, these are the probability, was a probability mass function in this case. This probability histogram, that's the probability mass function. It gives us the individual values and their probabilities of occurring. This gives us the individual values and their probabilities of occurring. Same thing as the table. But we could quite easily, that's not a subject for today, we could write that out in a different way, and instead of giving those values equal to, we could do this. And we will do that sometimes, just not right now. Bringing up the notion that there's different functions that we could write out that would uniquely determine the distribution, right? So if we have the function, we know what the distribution is. Okay, so we have a couple of important points here with our expectation and variance of discrete random variables. Characteristics of a distribution. Important characteristics of the distribution. And the expected value, or what we may call expectation of a random variable, the theoretical mean. So it's the theoretical mean, the mean of the random variable or the mean of its probability distribution, means the same thing. Okay, so we're going to represent this thing as with this expectation operator. So the expected value of x. It's not what we'd expect to see on any one trial or that kind of thing. It's what the theoretical mean, right? The expectation of x is the theoretical mean of the random variable, which we might also represent as mu sub x, or just mu. If we have one random variable, mu, the mean, the theoretical mean of the random variable. Mu is a parameter, right? Mu and expected value of x, these two things mean the same thing, right? Same thing. Okay, we got different notation for the same thing. Yes, we do. But the theoretical mean of the random variable, or the theoretical mean of its probability distribution, and that's a parameter, a characteristic of the distribution. We're going to pretend we know it for a little while, but later on, again, like with parameters, we're going to want to estimate that. We're going to want to estimate the mean, the theoretical mean of a random variable, this kind of thing. Okay, so to actually calculate it, we'll have different formulas for discrete and continuous random variables. And to calculate the expected value for a discrete random variable, this is the definition for the expectation of x for a discrete random variable. Every value of x times its probability of occurring and added up. The expected value of x, every value of x times its probability of occurring and added up. We might think of this as, well, it is a weighted average of the values of x weighted by their probabilities of occurring. And we are going to give more emphasis then to ones that have a higher probability of occurring. And if I just flip up here for 1 second, if we go up to here and I said, hey, let's figure out the mean of my random variable x here, it just wouldn't make any sense to say, 0 plus 1 plus 2 divided by 3, that's 1, that's my mean. It doesn't make any sense at all to do that because 0 has a much higher probability than the others. So we should be weighted more towards 0. 0 is happening a lot. The average value of your random variable x is not 1. It's a lot less than 1. We need to take into account the probability of each individual value occurring. And that's what the expectation does. So if we're going down here, we have our expected value, again, the sum of x times p of x. Each value weighted by its probability of occurring and added up. You might notice that over here I've got a capital X because we take the expectation of a random variable. So the expectation of a random variable. Over here I have a lowercase x because we actually need to put values of the random variable into the formula. So it's not a typo or a mistake or an inadvertent thing that I did. Over here, expectation of a random variable x. But to find that, we take each value of the random variable, multiply it by its probability of occurring, and add it up. This generalizes to other functions. The expectation of a function, g of x. So if we have that, we might be interested in, let's say, the expectation of the square of x, or the expectation of, depending on the situation we have, of the natural log of x. Just a function of x cubed, 1 over x, whatever it is, in a given situation, we might want the expectation of a function of x. And we do something very similar to what we did up here. You want the theoretical average values of that function of x. You take values of that function of x and you multiply them by the probability of each value of x occurring. So the value of the function times the probability of that value of x occurring. And similarly, we add that up over all x. So we're adding this up. Add that up over all x values, right? That's what we do to find this expected value of some function of x. Now, the next most important thing to us, the next most important characteristic of the distribution after the mean, say, in typical settings for us, it depends, exactly what you're looking for. But for when we're labeling and putting up characteristics of the distributions, we often want to talk about the mean, and we often want to talk about the variance. And that leads us to the standard deviation as well. The variance is the expectation of its squared distance from the mean. So the variance of a random variable x, by definition here, the expectation of x minus mu squared. Now, we're taking this random variable x minus mu. We can think of this, because we're squaring it, we can think of this as the average squared distance from the mean. The true theoretical average squared distance from the mean. And to find that, we're just applying this formula, this thing, and we're putting this in for g of x. So if we want this, and again, the expectation, we have the capital X here, and then this little mu. If we want this, to actually do that, we sum over all x values of this function, so little x minus mu squared, values of this function, but weight them by the probability of little x occurring. So x minus mu squared, getting from here, right? This is the definition of the variance of the random variable x. And we'd find it for discrete random variables this way, and continuous random variables is going to be a little bit different, but similar in spirit. This is going to hold for all random variables, this bit, but the math is going to change for continuous, and we're going to have to integrate. Okay, so this is the variance, which we might also label as sigma squared or sigma squared sub x. So you see either one of those. Sigma squared sub x is the variance of x, or I write it as the var x. Either one of these is fine. And if there's only one random variable, I might just leave out the x because there's no points of confusion. It's just the one, and just call it sigma squared. Again, this is a parameter of the distribution. A parameter of the distribution. How much variability there is in our random variable. It's the variance of your random variable x. And the standard deviation, you might be shocked to learn we're going to represent the standard deviation with sigma. And that is simply going to be the square root of the variance. So sigma, which is the true theoretical standard deviation of our random variable x, is the standard deviation, the square root of the variance, the square root of the average squared distance from the mean. And similarly to when we talked about this in discrete random variables, in descriptive statistics back then, it's sort of a little tricky to think of the standard deviation, but we'll look at some examples here in a minute. Okay, so that's the definition of the variance. That's just the definition of the variance of a random variable x. For discrete random variables, we can calculate it this way, just from our basic principles of what we learned up above with the expectation of a function of a random variable x. But I'm telling you, there is this handy relationship It is useful in calculations. It is useful in theoretical work. It is just something that comes up a lot. So even like for beyond stat 1, we use this in some statistical proofs when we need things. This is a useful thing to know. So the variance is this thing, and we can always calculate it like this. This is all true, right? Remember, this is the variance of x, but mathematically, I'm not going to prove it here, but it is true notwithstanding. This is equal to, mathematically equivalent to the expectation of the square of x minus the square of the expectation. Minus the square of the expectation. And this term here, if we wanted to think of it as mu squared, we could, right? If that's what we wanted. But the expectation of x minus mu squared, we could do it like this, but also works out to this, where it's the expectation of the square of x minus the square of the expectation. And quite often, this is a handy thing to work with, because we've already worked out the expected value of x, and then we just have to do the expected value of x squared. Just trust me on this one. It is handy to use this in a number of spots, and also surprisingly useful for some theoretical work at times as well. So handy relationship comes up a lot, not just in stat 1. So let's look at a couple of things here. So let's say we bought a novelty coin. Similar idea to the major defects, except just have a little bit of different probability here. Novelty coin, probability 0.6 of coming up heads anytime it's flipped. So just simplified scenario here. And we're going to let x represent the number of heads and the coin is tossed twice. So we're tossing this, and reasonable to think of our tosses as being independent here. And with the same logic I used up above with the defective and the major structural defects sort of notion, we have this. What are the possible values of x when our coin is tossed twice? Well, 0, 1, and 2. It's the number of heads. We could get 0 heads, we could get 1 head, we could get 2 heads. And if we're tossing them independently, the probability of getting 2 heads, 0.6 squared, right? And similarly, the probability of getting of 0 is going to be 0.4 squared. And if you're having trouble with this, go back in the logic that we used at the time up above, where I did that, discussed it when we were talking about the babies and the major structural defects. So this is the probability distribution of a random variable x. We could also call this the probability mass function, the various values of x, and their probabilities of occurring. One of the major characteristics of a distribution is its expected value. So if I want my expected value of my random variable x, the expected value of my random variable x, for discrete random variables, that's just the sum of x times the probability of occurring. And again, it doesn't make any sense for us to go, oh, it would just be 0 plus 1 plus 2 divided by 3. That makes no sense, because 2's happening a lot more often than 0, and it should have more weight in the calculations, which is what we do. So what we do by this, take the value of x times its probability of occurring. Value of x times its probability of occurring. So this is going to be 0 times 0.16 plus 1 times 0.48 plus 2 times 0.36. And I know from the nature of the problem here that that is going to be 1.2. But you can do those calculations yourself and see. Each value times its probability of occurring and add it up. On average, theoretically, we're going to get heads 1.2 times when we toss this coin twice. Okay, that's an important characteristic of a distribution. The variance of my random variable x. The variance of my random variable x. Okay, I can do it this way. Sigma squared, right? We've got this formula. It's a formula. Each value, 0, my first value, minus the mean, which we just found to be 1.2, squared, times the probability of 0, plus 1, the next value up, minus the mean, squared, times the probability of 1. 2 minus the mean squared times the probability of 2 here. And overall, if we did that, we'd get 0.48. The variance of x is 0.48. And the standard deviation is the square root of that, the square root of 0.48. And that's approximately, to 4 decimal places anyway, 0.6928. So another important characteristic of our distribution, the variance and the standard deviation. And if we wanted to, or like we're done, I figured out my mean and standard deviation, right? We've worked that out. I figured out the variance, so that's my variance, my standard deviation. But if we wanted to verify this, we could also see that sigma squared is also equal to the expectation of x squared minus the square of the expectation of x. This is true. And to work out the expected value of x squared, it's the expected value of a function of x. We apply that function to each value of x. 0 squared times 0.16 plus 1 squared times 0.48. Looking a little messy. Plus 2 squared times 0.36. That's the expected value of the square of x. And that is 1.92. That works out to that. You can verify for that for yourself. Notice, the expectation of the square of x is not the square of the expectation of x. They are different things. And in fact, your expectation of x squared can't be less than the square of the expectation. So this is not 1.2 squared. It's 1.92. And if we use this, 1.92 minus 1.2 squared, 1.2 squared is 1.44, and wait a minute, we're going to get 0.48. Oh, that's what we got already. We figured that out. Mathematically equivalent, and a handy thing to know. So this isn't the definition of the variance, but it is a consequence. This is mathematically equivalent to our first definition of the variance. Okay, so we need to be able to calculate those things, but let's just see. Let's just take a little look. We'll just try and get an idea of what I mean by this. If we did this is our probability histogram for that distribution. The values were 0, 1, and 2. 0, 1, and 2. And the probabilities we had are 0.16, 0.48, and 0.36. So this is the theoretical distribution of our random variable x. Over here, I simulated 1 million values from this distribution. Software is nice for doing this, right? So obviously the modern era, we can do this very, very fast, and I could do way more than 1 million, but I did 1 million, right? 1 million values simulated from here. And plotted the relative frequency, the proportion of times each one of these values happened. First, what do we notice? This proportion is really close to that probability, the theoretical probability. This proportion is really close to the theoretical probability. This proportion is really close to the theoretical probability. The law of large numbers tells us that has to happen, okay? That the proportion of times these things occur are going to get really close to the true probability of them occurring as the number of trials increases. We have 1 million trials here, it's quite a few, right? Not infinite, but quite a few. But also, my major point here, if we look at the sample mean, my sample mean of these values is really close to the expected value of x. It's what we would expect to get on average if we did trial after trial, repeated after repeated. If we took our ordinary sample mean after doing this a whole pile of times after drawing from this distribution, our sample mean is going to be really close to the expected value of x. The expected value of x is the true theoretical mean of x. Like what would happen if we went way out, like off to infinity in the limit? What would happen? The true theoretical average here of 1.2. Okay. Helps a little bit to have a little look, just a little bit of a feel. Hope that makes some sense with that, but just a couple of distributions to have a look. 4 discrete probability distributions and the mean and standard deviation for each one. So maybe this one is the simplest one to look at first. I have the numbers, whole numbers 0 through 9, and I've made them equally likely. And not going to do the calculations for you, but the true mean, not too shockingly, I think, is at 4.5. And the standard deviation is about 2.9. So that's the distance between the tips of the arrows there, 2.9. That's the standard deviation, a measure of variability. And if we looked at something like this, similar type of notion between these two, right? Having 1, 2, 3, and 4, and they're all equally likely. And again, here the mu is average of 2.5, but my standard deviation is quite a bit lower, right? Quite a bit smaller. There's not as much variability here relative to this one, say. And a couple of other distributions that, just to give us a feel for some other stuff, we have something like this. It's a symmetric distribution, right? The mirror images still left and right sides. And the mean here, because it's a perfectly symmetric distribution, we have our mean right in the middle, again, at 4.5. But my standard deviation here is 4.3. Like there's more spread, right? They're out towards the tail. So my standard deviation of 4.3 is bigger than it was here. Because we're getting these sort of extremes quite a bit more, various ways of thinking about it, but my standard deviation is a fair bit larger there. And then here we have skewness, little skewness, right skewed, like with histograms, same idea, right? Right skewness here. So maybe not quite so easy to see where the mean would be. We'd have to calculate it using the functions we gave above, but here we have a standard deviation of 2.4. So trying to just give you a little bit of an idea visually of what the mean and standard deviation means in certain spots. This is a basic thing with our intro to discrete random variables. Now we have a bunch of specific discrete random variable models that we talk about, like our specific distributions, like the binomial distribution, Poisson distribution, hypergeometric distribution, and there's many others as well. But we'll talk about some of those another time.